Okay, so it's time to go ahead and start. So the main thing we're going to talk about today is an FSM. FSM stands for finite state machine, and it's really what we work towards because the FSM contains both types of logic circuitry. So it contains combinational case circuitry that doesn't have memory, and then also sequential circuit that does have memory. So kind of, it's a device that incorporates both types of logic circuitry that we've talked about. And lab 6, lab 6 isn't due till the end of next week. Remember, lab 5 is the lab that's due this Friday that hopefully you got to start on, and you'll have time after today's lecture and activity to work on lab 5. But lab 6 involves an FSM. Also, the final project, as explained in the syllabus, and I'll talk about more about it next week. But the final project has 2 parts to it. There's an individual part, and that individual part contains an FSM. And then there's also a team portion of the final project where you decide, your team decides, what they want to do for the project. And one of the requirements of the final project team is that it has to have an FSM. So FSMs are really important. In fact, I put this diagram of the CPE133 microprocessor on each table again. And if you look at this diagram up in the upper right-hand corner, CU FSM, that's control unit finite state machine. So, we pointed out earlier in the quarter that there's a decoder as part of the microprocessor, that's control unit decoder, and that's outputting, or its outputs go to the select line of all the muxes in the microprocessor. Well, if you look at the outputs of this FSM, most of the outputs, you'll see the word write, or you'll see WE, where the W stands for write, or you'll see an RD, which stands for read. And when you take that class, you'll learn that, write is just like an enter or an enable, and read is when you're getting data from a device, and write, like an enable or enters, when you're putting data in. Well, the FSM is controlling all the reads and the writes of all these different components. And you'll learn again in that class that those signals are time critical. Okay, so the FSM is taking care of all the time critical signals in the microprocessor. So, I just point this out at the start because understanding an FSM and knowing how to model it in Verilog is not only important for like 3 assignments in this class, right? The last lab assignment, and also both parts of the final project, but you'll also, deal with an FSM using CPE133. So, like I said, FSM is the big topic today, but before we get to the FSM, there's just a couple of other modules that I want to go over. These modules, thank you. But one of them is part of Lab 6, but it's also a module that often comes up in a final project team. And then the second module, same sort of thing, that often it's used in the final project, based on what a team decides to do. So the first one here that is part of Lab 6, and also, like I said, comes up a lot in team projects, is a clock divider. And then the counter is one, won't be in Lab 6, but comes up in team projects, and also is part of CPE133. Okay, so I just want to go over these 2 modules, and then we'll talk about the FSM. Also, I know people are always curious about when you get the midterms, graded. I got about halfway done this weekend, and I know I won't have enough time tomorrow to finish them. So I need another weekend. So I will have your scores a week from today. It will be the Tuesday of next week. Okay. All right. So also on your table, there's this handout here that has some code on it from System Verilog code. So you may want to take a look at that while I'm talking about what the clock divider does. I was hoping again, by putting one copy, maybe you can take pictures of it and look at it on your phone, or you can share it with one another and have like a group view of everybody looking at it at the same time. But a clock divider module, as the name implies, it divides the clock's frequency. So often we'll have a frequency like what's on your basis board. We talked about this. Thought I tested that out before class. I must have had the wrong one. Okay, here we go. So I think we talked about this last class or sometime last week that the basis board, it has a clock frequency of 100 megahertz. And often you want to operate something at a lower frequency. So when we take a higher frequency and convert it down into a lower frequency, and we say we're dividing that frequency. That's where the name clock divider comes from. So if you look at the inputs and outputs here, just one input, one output, right? Our input here is clock, and then our output is S clock, where S stands for slow clock. We're going to decrease the frequency of that 100 megahertz. So we talked about this at some point last week. We talked about the relationship between the period of a signal and the frequency of a signal. What's the relationship between the two? Yeah, it's just reciprocal, right? So frequency is just reciprocal of period, right? Period is reciprocal of frequency. So if you have 100 megahertz signal, like the clock on your basis 3 board, what would the period of that be? In fact, when you do a SIM file in Bravado, you know, you put that number sign 10. What does that number sign 10 mean in the SIM file? It obviously means 10, but 10 what? Didn't we talk about this last week? I could have swore we don't remember. Yeah, exactly, nanoseconds, right? Remember that your test cases in your SIM file, you know, you have number sign 10 test case, right? Number sign 10 test case. That number sign 10, that's 10 nanoseconds. Whatever follows the number sign in the SIM file in Verilog, that's in nanoseconds. Okay, so we're separating each test case by a clock cycle. Okay, so 10 nanoseconds. And what's nano again? 10 to the what? Minus. Very good green. Let's see if I can get a better green. Or maybe we'll just go with blue. Okay, you're going to see how this ties into that code coming up. Also, if you look at the code on that handout, you'll see at the very top, you'll see this number sign and then in parentheses, parameter max count equal to 1. This is something that you can do in System Verilog, is that you can basically define a variable. So what follows parameter is max count. This is just a variable. Okay, that we can easily change the value to. But where you define it, you see this equal 1. This is what the default value would be. Okay. So whatever you list within the parentheses when you define the variable, that's going to be its default value. And then if you want to change it, like say you wanted to change it, you know, to some other number, like say you wanted to change it to 50 million. Now, you could just change the default value to 50 million. But the other thing you can do to change the default value is change it in your structural model, okay, where you're making the connections. Right at the beginning of the line where you're making the connections to that file, you could just put number sign with the new value that you want that variable to be. Okay, so this is just something in Verilog that sometimes is handy to do. It's not like required or anything, but sometimes people like to define a variable like that because it gives them some flexibility. But maybe like in your design, maybe you have multiple block dividers, right? That are dividing by a different amount, and therefore this max count would be a different number. Okay, and you'll see why that's true when we go through this example. Okay. All right. Also, if you look at that handout with the code on it, you see count. How many bits is count? Yeah, tell me looking at the code there. How many? 30, right? Because it's 29 to 0. So the most significant bit we're calling number 29, right? Least significant bit, we always call 0 except Dr. Mealy and universal segment module is the opposite, right? But normally we always say least significant bit 0, most significant bit is the highest number, which is 29 in this case. So yeah, it's 30 bits. A lot of bits. So what would the range of numbers that I can represent with 30 bits? This is unsigned, right? It's just an integer. Okay, we're just talking about unsigned here. So if I have 30 bits, I can go from what number to what number? Or how would you figure out? Well, you should be able to tell me the low number, because for any unsigned, what's the least number I can represent? If I can't represent negative, zero. Yeah, just 0. So that's right, 0. But how would you figure out the top number? To be what? Is that it? -1, right? Because anytime I'm doing this with a lot of bits, I think about a small number of bits, right? Because if it was 4 bits, it would be 0 to what? 15, right? 15 is 2 to the 4 minus 1. Right? So this would just be 2 to the 30 minus 1. And that's a big number. I can't remember. Like 1,073,000 or 1 billion, I should say, 73 million. 741,823. It's 2 to the 30 is 1,073,741,824. So -1, 823. Actually, this brings up something that isn't really required to know in this class, but you'll learn this if you don't already know it. Like the first day of the first week of CPE133. And that's, in base 2, 1K does not equal 1,000 like it does in base 10. Like when we say 1K in the digital world, we don't mean 1,000 even. Does anyone know what we mean by 1K in the digital world? So it's 1024. Exactly. It's 1,024. Do you know why it's 1,024? That's a power to. Yeah, because it's equal to 2 to the 10. Right? To take 2 to the 10, it's 1,024. So, when someone in the digital world talks about 1K, they mean 1,024. They don't mean 1,000 either. Okay, so 64K. All my markers are all getting worn out here. 64K in the base 2 world doesn't mean 64,000. It means 64 times 1,024. Okay, which is like 65,536. Okay. So I've always said, like, if you get offered a job and they say your salary is 64K, you should say, well, can I have that in a base 2 cents? Right? Because you pick up another 1,000 some odd dollars, right? I tried that at my credit union one time, but they didn't understand. They thought I was crazy. They don't understand base 2 at my credit union. So I didn't get the job. But it's the same sort of deal with 2 to the 20. 2 to the 20 is 1 meg, but it's not 1 million even in the base 2 world. It's actually like 1,048,000. Because if you do 2 to the 20, you'll see it's like 1,048,536, something like that. And same sort of deal here with 2 to the 30. 2 to the 30, that's a gig. Okay, but it's not a billion even in base 2. It's this number. Okay, and that's because again, 2 to the 30 gives you, more than a billion. Okay, so like I said, this isn't so important for this class, but I figured since we're talking about a big number here, and you'll have to know this for CPE133. It's a big time to talk about it. Okay, so now if you take a look at this handout again. Okay. If you take a look at this handout, you can see here, like we said, count is defined to be 30 bits. Also, after where you see count, see how there's an equal sign and 0, that's initializing count to 0. Okay, so you see here, count is initialized to 0, and that same line where it's defined as 30 bits. Okay. So to see how this module is dividing the clock frequency, okay, how this code, how it works, let's just do an example. Let's say that we change max count to 50 million. So like I said, one way you could change it is just up here, just change the 1 to 50 million. But another way you can change it is to leave this 1, but then in the structural model that this is part of, where you're making the connections, you could just put number sign with the new number right before you start making connections for that module. And that would also change that variable to the new number. Okay. All right, so now if you take a look, you can see there's an always FF block, and you can see it's sensitive to the positive edge of the clock, right? So on every 0 to 1 transition of this 100 megahertz signal, that's when this if statement that's when the code between the begin and the end is going to be a value, say on every positive edge of the clock. So you can see the first thing is that count is incremented by 1. Okay, so it starts at 0, gets incremented by 1, and be 1, then it goes to the if statement, and the if statement is going to compare that count against the max count that we made 50 million. So obviously, that if statement's not going to be executed until count equals max count. So what that means is that as the input, right, as this 100 megahertz square wave is going up and down, up and down, up and down at 100 megahertz, well, at every positive edge, S clock for the first 50 million is just going to stay low, right? Because it's not until the count gets up to 50 million where it equals max count that now the if statement is executed, and when the if statement is executed, it initializes count back to 0, and then it inverts S clock. So you see S clock is going to stay low for 50 million clock pulses, right? Each clock pulse is 10 nanoseconds. So if you take 50 million times, that's a 6. That's supposed to be 6. Right? 50 million times 10 nanoseconds, right? Because each clock pulse is 10 nanoseconds. Well, this comes out to 500 milliseconds. How many seconds is 500 milliseconds? Milliseconds would be what in seconds? Would be 5? 0.5. So you see, S clock is going to stay low for a half a second until it finally inverts. Right? S clock inverts, becomes a 1. Right? And since we initialized count back to 0, now S clock is going to stay a 1 for 50 million clock cycles before it inverts again. So you see, now it's going to stay high for half a second, right? Before it goes low, and then it's going to stay low for half a second, go high half a second. Okay, so you see how we're slowing down the clock using this code here? right? So, you know, with this number here, this 50 million, I now have a period of what? Because it's low for half a second, then it's high. Now, this wasn't obviously drawn to scale. But this is low for half a second, then high for half a second. So the period is 1 second, and the frequency of something with a period of 1 second is 1 hertz. So this actually took 100 megahertz and made it 1 hertz. And if you wanted to make it some other frequency, right? If you wanted to make it some other frequency, well, you would just have to figure out what the period has to be and what my new max count number has to be to get that period. Okay, so, you know, this is an example to go from 100 megahertz down to 1 hertz, but if you understand this example, you can go from any frequency to any. Right? Okay, so is there any questions on the code or what we did with the problem? Like I mentioned, a clock divider is part of Lab 6. Now you're going to be given the code actually for the clock divider because it's written in a different language. It's written in VHDL, if I remember correctly. But no matter what language, whether it's Verilog or whether it's System Verilog or whether it's VHDL, which is another type of software that can model hardware, in order to change what you divide by, it's just changing a number. And you'll see, and when we get to Lab 6, we won't get to Lab 6 today, probably on Thursday we will. But when we get there, I'll point out the number that you would have to change in order to change the divide by. Okay, because, you know, like I mentioned, a lot of times in the final project team portion, a lot of times a group will need a clock divide, but they'll need a different number. They don't want to divide by what's in that clock divider for Lab 6. They want to, you know, use something different. And this is how you would figure it out. You know, this example is an illustration of how you would figure out what number. Okay. So any questions before we move on?
Is it possible to adjust the clock speed without using a circuit?
Oh, that's a good question. You know, one thing you learn as you get older is that there's usually more than one way to do something. I would say this is probably the most popular way of doing it, but yeah, I don't doubt there's other ways to do it. Yeah, as you get older, you always, I think what you learn is, you know, there's more than one way to do many things. And then the other thing you learn is how much, what is it? Like the more you know, the more you realize what you don't know. I think that's also true. And I think it's also true that most things are gray, they're not black and white. That's just philosophy according to Gary Brooks. Okay, so you want to move on? All right, the next thing, and you know, this is going to be very brief here because it's just one main point I want to make, and that's counters. And there's a counter that's part of that microprocessor in CPE133. Like again, if you take a look at this diagram, down in the lower left-hand corner where it says PC, that stands for program counter. That's a type of counter. Okay, and that's what I have up here in a modified form as an example. As you can see up here on the board, what's different is I'm not including the mux. Okay, I'm just looking at the counter itself. Okay, you all know, or at this point, everyone should be familiar with how a mux works. Right? The mux here is just determining, you know, which of these how many inputs are there? Which of these 6 inputs gets passed at the output of the mux and then goes to the input of the counter. Okay, but the main point that I want to make here is that a counter is just essentially a register whose output will increment by a certain amount. Okay, so like this counter that's part of CPE133, this part right here that you see, the PC out, PC in. See, PC out is just like Q of a register. And PC in is just like the D input of a register. And PCWR, which WR stands for write, that's just like enter or enable of a register. And then PCRST, that's reset. well, that's also just like reset of a register. So a big part of the counter is that it's the same as a register. In fact, in Verilog, you would model a counter just like the register. You know, like the register that you're going to use, the code, the Verilog that you're going to use to model the register for lab 5, that would be exactly the same code that you would use to model this counter when you take CPE133. But in addition to the register part, a counter, its output is going to increment. Okay, sometimes it increments in like equal installments, if you will, like, you know, for every clock pulse, it will increment 1, or for every clock pulse, it will increment 4. Sometimes a counter goes in non-sequential order. In fact, we're going to see an example of that, how an FSM can be used to do that. Okay. But the key point here is that a counter is basically a register plus, okay, where the plus is that the output is going to increment in some amount. Okay, so it's a register. In system Verilog, it's a register plus to get the increment amount like this +4. Now, when you take CPE133, you're going to see why this is +4. Okay, there's a very important reason why it's that number. Okay, until you take the class, it really doesn't matter. For this discussion, it doesn't really come into what I'm trying to point out. See, the thing I want to point out is the additional Verilog code that you would need in order to model this counter compared to the register is just one assign statement. See, all you would need in addition to the code of a register is you would have to have an assign where whatever you call this side of this +4 module, you know, and I've got it as T2. You would just make that the other side, whatever you call the other side, +4. Okay, so you would have your, you know, code for the register, and then when you connect this up in your structural model, in the structural in your structural source code, you would have this assigned, which gives you the increment between the output and the input. Because see, initially what would happen is you would reset this so the output starts at 0, and then every time this write gets active, and this is an active hot, so every time after you reset it, that you make the PC write input equal to 1, that will take the previous count +4 and put it at the output. So now your output is, you know, what you had previously +4, right? So it'd be 0 + 4. Right? And then you do another PC write, and it will take what you had previously, the 0 + 4, and increment it another 4, so you go 4 to 8. Okay, so on every time that you activate this write input, now, the other thing that you'll learn in CPE133 is that this write is synchronous. It's a synchronous write. So it not only has to be active, not only has to be equal to 1, but you have to have the clock edge, the 0 to 1 transition. So every time this write is high during the clock edge, that's when the increment will happen. That's when your PC in will now be a PC out, and you get the +4 from the previous value. Okay. So, like I said, main point here, and this is something I would recommend that you kind of retain when, you know, from this class. So when you go into 233 and the professor starts talking about a counter, the first thing that should pop up into your head is, oh, a counter. It's just like a register, but the output increments by a certain amount. Okay. And also, sometimes in the team project, again, depending what people decide to do, sometimes people need a counter. Okay, and if you need a counter, this is one way to do it. Now, going back to Ben's question earlier with the clock divider, I don't want you to think this is the only way to do it. I mean, there are other ways to model counters too. Okay, but I kind of like this representation because, again, it just shows that a counter and a register are essentially the same thing. Okay, right? It's just the counter has an added thing, right? That increment by so much. Okay, so any questions on a counter? Okay, so finally to really the main topic of the day. And like I said at the beginning of class, FSMs, finite state machines, very important. Okay, it's going to be part of lab 6. It's part of both parts of the final project, and it's also part of CP233. And just in practice, FSMs are very commonly used. Okay, it's when you can really start doing interesting things. Okay, so first of all, some basics, and up at the board, this is the high level block diagram of an FSM. So there's 3 main parts to an FSM. Okay, as you can see here. There's a next state decoder, there's state registers, and there's an output decoder. So out of these 3 blocks, one of them is sequential because one of them has memory. Which one is it? Which one? Is it the decoder? What would have memory? Registers, right? Remember registers? Registers have memory, right? They store. Also, what else gives it away? The clock, right? Sequential circuits have a clock. Combinational don't have clocks. So yeah, this is sequential here. Okay. It has memory. All right, but how about the decoders? Are they sequential? No, those are combinational. Okay, no clock. And so these are combinational. I'll just put combo for combinational. Okay, so like I mentioned earlier, that's why FSMs are discussed towards the end of an introduction class like this, right? Because it contains both of the typologic circuitry that we discussed, right? We started off talking about combinational at the beginning of the quarter, and then just last week we started talking about memory and sequential. Okay, so you see the reason why a finite state machine has both types of logic circuitry is, first of all, the state registers that have memory, they hold on to the state registers have the information where we're at. Okay, like where we're at in some sort of sequence of events. The next state decoder determines where we're going. Okay, so the state registers have a state, where we're at, and then the next state decoder determines, okay, where we're going from that state that we're at, where the next state is. Okay, that's why it's called the next state decoder. Kind of makes sense. Okay. Now the output decoder, it's determining as the name implies, it's determining the output. And this is where having 2 types of FSMs come into play. Okay, there's 2 types. You might have noticed that before I wrote combo and sequential and memory and combo over there in blue, there was only these 2 lines that were in blue and everything else was in black. And that's because the 2 FSMs we have, one's called a Moore, and the other's called a Mealy. And I know someone's going to ask eventually, so I'll just answer now. As far as I know, there's no relation to Dr. Mealy. It's pure coincidence. It's a different Mealy that this is named after. But anyway, there's these 2 types of FSMs, and the more the output of a Moore FSM depends only on the state. It only depends on the state. The Mealy, the output depends on state and external inputs. So the more FSM is just what's in black. So like these two lines right here are not part of a more FSM. A mealy has what's in black and also these two blue lines. Okay, so the mealy would have the black and the blue. Black and blue lines. Okay, because if you look over here where the output decoder is, see if it's a more, the inputs of the output decoder are only coming from the state registers, right? And that's where we're at. That's the state we're at. Okay, if this is a mealy, well, you not only have the state registers inputted to the mealy output decoder, but you also have these external inputs coming in too. Okay, so Dr. Benson, better. Markers are not good today. Dr. Benson, he has this saying that I think helps with this, and that's more is less. Right? Because a more only depends on the state registers. The mealy, it's more than the more, right? Because the mealy depends not only on the state registers, but also on external inputs. Okay. Now, this being said, both the more and the mealy can be used to do the same thing, right? You can do an FSM with a more design. You can do an FSM, doing the same design, but it's a mealy. Okay, so sometimes one of these will give you less states than the other. And if you're really concerned about being efficient and doing things with the least number of states, well, you would choose that one. If you're not so concerned, like if there's an extra state, well, then it just becomes sort of personal preference, which one you use. Okay, but they both can be used to do the same thing. Okay. All righty. So, any questions up to this point? I mean, this is just some basics about FSMs. We're going to get to more specifics through an example. The next thing to come up is a state diagram, because that's where you always start with any sort of FSM design. But I think this would be a good time to take a break, because to do the state diagram, then also show you the code that you need in Verilog is probably going to take another at least half hour. So why don't we take about a 5-minute break, maybe till 5 of, and then I'll continue on. Okay. And also I got to turn the camera before I forget. So you can take about 5 minutes or so, and I'll start up again.
What is this symbol right here?
That's a capital T for period, like period of a signal. Are you pointing at this?
Yeah, right.
Yeah, that's a T, like a capital.
Oh, is that inside? What is that?
Yeah, because period is the kind of takes for every form. So it's one cycle.
Oh,
Oh, it's just like we talked about, period is reciprocal of frequency.
oh, that's it, just back to the time. Oh, thank you. Yeah. That was just like right there. Oh. I took one, now it's three. But it's a lot of work. A lot of work. It depends. Martin, I love something to do with an election. No, yeah. Well, yeah. That's what G, oh, it's G. Yeah. People been telling me people on instead of biology. You should. I don't want to take biology because there's a way you should know like with yeah. I would say keep it on five. Sorry. You not working on without cells more than it's like I think she does. Yes. Everything make sure it's in your I would like to get a really big hole. On both spots that
Okay, it looks like it's 5 of, so let's go ahead and continue on now. So, like I said, we're gonna go through this example. Okay, it's an FSM counter that can do this sequence here. You know, it starts at 2, then 0, 7, 5, 3, and then it just repeats. Now, there's nothing special about using a counter as an example because you can design virtually, anything with an FSM as long as you can, represent the states of whatever you want to design and put it into a diagram called a state diagram. Well, from that state diagram, you can then, create an FSM. And I'm going to show you how to do this with this example. But like I said, I could have picked. There's probably an infinite number of examples. I don't want you to think this is like, anything special. Right? I just picked something. Okay. So like I have here, no matter what you design with an FSM, you want to start with a state diagram, and all state diagrams should have a legend. Okay. And what's pretty standard, and just like most things, I wouldn't say, all of this is written in stone, but it's pretty standard that for a state diagram, in your legend, you have a circle. That circle represents a state. Okay, and then usually at the top is the name of the state, and you can call it whatever you want. And then what goes here, okay, what goes underneath the name is if you have a more output. Okay, now in this FSM counter example, because all our numbers here, because the largest number in our sequence is 7, what's the minimum number of bits I need to represent 7 in binary? 3. Okay, because of that, what I'm going to label my more output is just, B2, B1, B0, right? The 3 bits that represent the binary of each of the numbers that's in my count. Okay. Now, also in the legend, there's this arrow, right? This curved arrow. This just represents a clock transition. Okay, now we're going to add to this legend coming up, but anyway, this is where we're starting. Okay. All right, so now I'm going to do my state diagram. And each count, 2, 0, 7, 5, 3, right? We got 5 different numbers. Each count's going to be a state. So I'm going to have 5 circles. It doesn't matter, how you orient these, but I'm going to orient them like this. Okay. And I'm going to call this first state, state A, and I'm just going to use STA. Again, you can name it whatever you want, but I'm just going to use letters. Okay, so state A, state B, state C, state D, state T. And then state A, the number is 2, so in binary, right? 0, 1, 0. Then all zeros here. Then 1, 1, 1. 1, 0, 5 for 5. And then 0, 1, 1 for 3. Okay, so you see state A, what the count is, state B, what the count is, so on. And then the arrows show from what state I'm going, what state I'm starting at and what state I'm going to. Okay, so since I'm going 20753, it would just be, I'm going state A to state B, state B to state C, C to D, D to E, E to A, right? Because I'm just going to repeat once I get to state B. Okay. Now, when you don't have anything on a clock transition like I have here, that's called an unconditional transition. Okay, so because, and you're going to see, I'm going to modify this coming up, okay? But when you don't see anything next to one of these transitions, it means it's unconditional. Okay, which just means that, when we're in state A, when the next clock edge happens, either 0 to 1 transition if it's rising edge triggered, or 1 to 0 transition when it's falling edge triggered, because the FSM has this sequential portion to it, right? FSMs are triggered just like registers and flip-flops are, right? Okay, so you have like rising edge triggered FSMs, you have falling edge triggered FSMs. Okay, so if it's a rising edge on each rising edge, that's when the transition would happen. Okay, unconditional. Okay, so everybody get what, because like I said, I'm going to modify this coming up. Okay, but the way it's drawn right now, it would be unconditional transitions, right? It's just going to go from one state to the other on every clock edge. Okay. All right. So I'm going to modify this, but before I modify it, any questions? Everybody's clear up to this point? Okay, now I'm going to modify. One thing I'm going to do is I'm going to add a reset. And this reset, it's active low, right? That's what the bar means. Remember, we talked about this before, like in timing diagrams and like on block diagrams, right? The bar means active low, right? It doesn't mean not. Okay. But one thing that's not shown on a diagram that you would have to state is whether this is synchronous or asynchronous. We're going to make it asynchronous. Now, I want to put a disclaimer on this, okay? And that's most resets in practical systems are synchronous. And in fact, that microprocessor that you build in CPE133, all the resets are synchronous in that microprocessor. Okay, there's some advantages to having synchronous resets when you have multiple modules as part of a system. Okay, because if they're synchronous, they're likely to all be reset at an exact time as opposed to when they're asynchronous. Okay, but the reason I'm making this reset in this example asynchronous is just to show you how to handle an asynchronous input in Verilog when we get to that point. Okay, but I just want to point that out because when you take CPE133 and the CPE133 professor says, oh, resets are always synchronous, don't go, well, hey, Perks, told us it was asynchronous because he did an example, right? I'm just doing this for example purposes, okay? All right, just want to make that clear. Okay, the other thing we're going to do to modify this is we're going to make the clock transition conditional instead of unconditional. And it's going to be conditional based on an enable input. Okay, so that the EN here stands for enable. Okay, so when the clock transition is not unconditional, then there'll be some input, some name that you put here by the arrow. Okay, so first thing is, and I just decided this, right? You could decide something different if you were doing this, but I decided that when the reset is activated, so when our active low reset is activated, it will take us to state A. So the way you would show that in your state diagram is you would just show an arrow like this. Okay, that when reset's activated, it's going to take us to this state. Maybe when you do a state diagram, you'll pick a different state. I picked state A. Okay. And the way the enable is going to work is when the enable is active, and this is active high, right? Because there's no bar over it. well, we'll continue in the sequence. When the enable's not activated, we're just going to stay in the state we're at. So the way you would show that in a state diagram is for all these transitions that go to the next state, you would just show enable high, enable high, or you could put enable equal to 1 if you wanted to, but it's understood if you don't put the bar there, it means when it's high or 1. And if enable's not high, right, if it's low, we're just going to stay in that state. Right, so you see the way we would show that is just an arrow going back to the same state. All right, so you see what this is telling us. If we're in state A, on the transition of the next clock pulse, if enable's high, we're going to go state B. If enable's low, we're going to stay in state A. All right, when we're in state B, on the next clock edge, if enable is high, we're going to state C. If enable's low, we're staying in state B, and so on. Okay? Does everybody see what I did there? All right, now we're going to add something else. The next thing we're going to add is I'm going to add another output. Okay, remember, in this, what we have so far, these actual numbers in our count, they're more outputs because they're only depending on the state. See, any output that only depends on the state, that's what we put in the bubble. But remember, there's another type of output. Okay, there's a mealy output. Okay, and in the same design, you can have both outputs. You can have a more and you can have a mealy. And if you have a mealy output, which not only depends on the state, but it depends on external inputs, like enable. Enable would be an external input. Well, mealy outputs in the state diagram, a mealy output we put underneath any external inputs like enable. So in the legend, if you have a mealy output, you put it here, right? So this is where mealy output goes. And again, a mealy output not only depends on the state, but it also depends on either an external input singular or external inputs plural. You could have either. Okay, so what I did to modify this to show a mealy is, let's say you know, we have some output device, let's say it's an LED, and we want that LED to indicate when the sequence starts and when the sequence ends. Okay. Well, I'm just going to call that output LED. So now, in my state diagram, when the sequence starts, so right here, when we go state A to state B, that's when the sequence starts, right? Because this is our starting point, and then this is our first transition. Well, that's when I would light up the LED. Okay, if I'm just staying in the same state, like the same initial state, well, I don't want the LED to light. Right, so, right, and again, here, the assumption would be that LED is activated by a 1. Right, so LED lights when it's a 1, LED doesn't light when it's a 0. Okay, so I want the LED to light when the sequence starts, and I only want the LED to light again when the sequence ends. So it'd be LED 1 right when the sequence ends, but everywhere else I want the LED to be on, right? I only want it to be on when it starts and when it ends. So everywhere else, I would just put not LED. Hopefully I'll get them all. If I miss one, let me know. Yeah, I got them all. Did I get them all? It'd be off here, off, 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 off. Right, it's only on when the sequence starts and when the sequence ends. Okay. So, again, just to summarize the important points. The circle in the state diagram represents a state. Inside the circle go more outputs because more outputs only depend on the state you're in. Okay, there's a name, right? Name could be anything. If you have something like a reset, this is how you show it. The arrow means a transition. Sometimes you can have an unconditional transition, right? It's just going to happen no matter what once the clock edge happens. Okay, and you don't show anything if that's the case. If it's conditional, then there's some input that's the transition depends on. You just put it right next to the arrow, like I did here with enable. And then if you have any sort of mealy output, again, the difference between a mealy and a more output is the mealy depends on not only the state, but also external inputs or external input. And you put in your state diagram, you put the mealy output underneath whatever input you have on the transition of the clock. Okay, the most common error people make is they get the mores and the mealies mixed up. Like they'll put the mealy in the circle when it shouldn't be there, and they'll put the more outside the circle when it shouldn't be there. That's the most common error that people make. Okay, but I think when we write the code, you'll also see the distinction between more and mealy. Okay, so any questions on the state diagram? The next thing before we do the code is, let's look at what the high-level black box diagram would look like. High-level black box diagram. This is our FSM counter. So what kind of inputs do we have here? There's one that should come to your mind right away since this has memory, right? It has sequential. So what do you have to have as an input? Yeah, clock should come up right away, right? Okay, but what other inputs do we have here? All you gotta do is look at the state diagram. What are inputs in that state diagram? Resets an input. What else? Enable. Yeah. Okay. And what would our outputs be? Yeah, LED. That's the mealy. More output, which is the count, right? We call that CT. And how many bits is our count? 3. So we'd have to put a slash there. So you see, once you have a state diagram, right, you can go right to the high-level black box diagram because you know your output's going to be here, right? The more output's going to be there, then the rest are your inputs, and then you got to add clock again, clock because we have registers. Okay. All right. So everybody good with state diagram and the high-level black box? How you get it? Really good. Okay. So the last thing here before we talk about the activity is the Verilog code. Okay, how you model FSMs in System Verilog. And the good news is, once you have a state diagram, it's pretty cookbook how you write the code. Okay, usually if someone has difficulty with FSMs, it's more the state diagram, getting the state diagram correct. I mean, this example I think is fairly straightforward. That's because, you know, it's the first exposure you've had to state diagrams. But state diagrams can get a little tricky. Okay, Lab 6, which I'll talk about on Thursday, where you're going to build a sequence detector. It can be a little challenging for some at first, right? But like anything, you know, I think it's similar to Carnot maps. You know, once you get the hang of it, it doesn't seem so bad, but at first it seems a little weird just because it, you know, it's something you haven't seen before. Okay, but as far as writing the code, once you have the state diagram, it's pretty cookbook. So the first thing is, you know, like always, you know, you give your module a name. I call this FSM counter. Then you would just declare your inputs and outputs like you've done. There's nothing different about that. Okay, so that's why I didn't write anything. Okay, then comes something you haven't seen before, right? After you declare your inputs and outputs, you then type in this code. This is type definition, you know, type def. Def is short for definition. And then enum is short for enumeration. And what you're doing here is you're declaring your states. Okay, so here we have 5 states, right? State A, B through state B. I wrote state, FTA for state A, STB. You would just continue STC, STD, STB. I just ran out of space, so I didn't write those. That's what I mean by the 4 dots. You would just name the other 3 states, and then you put that in braces, as you see here. And then outside the braces, you put states, and then a semicolon. And then you follow that with states PS. PS stands for present state. Okay, so PS equals present state. And NS stands for next state. So basically what this code is doing, it's defining those states that are in your state diagram. Okay, so that's what comes after declaring the inputs and outputs of your module. You have to declare your states. Now, there's another way of doing this. In fact, this is, I think, the most effective way. Okay, there's another way to do this that I'll show you when I show you the activity, because the activity, you're doing essentially what we did here, but in the reverse direction. See, I'm going from the state diagram to the code. The activity is you're given the code and you got to write the state diagram. You got to go the other direction. Well, when we look at the activity, you'll see that these 2 lines are different. Okay, and I'll explain when we get to that point why they're different, and I'll also explain why I recommend this way of doing it. Okay, so we'll come back to this, but anyway, again, these 2 lines are basically declaring, defining, however you want to put it, the states that are in our state diagram. Okay. Okay. Then the next thing that comes is an always FF block. Okay, so always underscore FF. So I want to make sure I get the syntax right. Then the @ symbol. Okay, then inside the parentheses here, we're going to have positive edge clock. Okay, that you've seen before. But then, and this is how you get an asynchronous input. Okay, then we're going to put neg edge reset. Okay, so, you've seen this before, right? Because we had always FF where we just had the positive edge, right? Positive edge of the clock. And remember, what's inside the parentheses here, that's called a sensitivity list, because whatever's in this, whatever in this sensitivity list, that's when the always FF block is going to be evaluated. So if you only have a positive edge clock inside the parentheses, this always FF block only gets evaluated on every positive edge of the clock. But you see, I added this neg edge reset because I also want this always FF block to be evaluated on the negative edge of reset. Okay, and as I'll explain coming up here shortly, that's what gives us an asynchronous reset. Okay. All right. So after the always FF, you got to have the begin for that block. So begin. And now we're going to have an if statement. Okay. If reset is low. Okay. What do we want to happen if, oops. Yeah. If reset is, no, actually, I can't do that. What do I have to put for a bar in Verilog? Say that again. Well, tilde is for not if you have like a Boolean expression, what's called bitwise, but it's something different when it's a in explanation. Okay, you could also, to the side here. In fact, this is what I have in my notes, but I like doing it this way now. But you could also, instead of having exclamation RST, you could also do RST 2 equal signs and then 0. Okay, so either this or this will work. Okay, but the tilde won't work because tilde is only when you're doing an equation, Boolean equation. It's called bitwise when you have an equation. Okay, so looking at a state diagram, when we have our reset activated, what do we want to happen? Right there in the state diagram, what happens if reset's activated? It's low. Right, goes to state A. So what you write in the code is you assign present state. Now, this isn't an always FF. So remember, this gets into the arrow or just the equal. Remember when it's in an always FF and you're assigning an output? you want the arrow, right? If it's combination, you want the equal. So you would assign present state to state A. And this needs a semicolon. All right, so this is what's going to take us to state A if reset's low. And else, we want present state to be assigned to next state. Right, because if we're not resetting, then wherever we're at, we want to go to the next state. And what's going to determine the next state is combinational. So what's going to determine the next state, as you're going to see, is going to be part of an always comb block. So when you're designing an FSM, and this shouldn't be a surprise based on that an FSM is made up of sequential and combinational, well, your Verilog code is going to have an always FF for the sequential, and it's going to have an always comb for the combination. Okay, we got the semicolon, then we want to end this. Okay, so this here, this code right here in the always FF, that's taking care of the state registry. Okay, that's the sequential part. Everything else now is going to be combinational. It's going to be in an always comb. And, you know, for essentially every FSM that you design, this is all you need in the always FF. You know, if you have a reset, you have that, and then it's just else you're going to the next state. You're assigning present state to the next state. Now, see, the reason why putting the negative edge reset here makes this asynchronous is because just think about it. If this wasn't here, right? If I only had positive edge clock, well, then the reset's going to be synchronous, right? Because the only time that if statement gets evaluated, if you only have the positive edge clock there, is on a 0 to 1 transition of the clock. So it would just check whether reset was low at that time of the clock, which means it's synchronous. But now when I add this, it's evaluating this if statement when the reset input goes low, right? On the transition of the reset going low. So on that transition, it checks, and it's going to be low, right? Since it was transitioning low, and then it's going to reset. Okay, so having the negative edge clock reset here, that's what makes this asynchronous. If it's not there, then the reset would be synchronous. Does that make sense? Now, one other thing I want to mention here, and again, this is just to prepare you for CP233. In CP233, there is one of the modules. It's the thing called the reg file, if I remember right. Let me look at this real quick. Yes, it's the reg file. When you take 233, you're going to learn that there's another way to do an asynchronous reset that's particular to that reg file module. Okay, you'll see that for that particular module, you can do an asynchronous reset by doing an assign statement instead of what you see here. Okay, I'm just mentioning that in passing, just so to give you a heads up. But this is the most usual way, if you will, of doing something asynchronous. All right. Okay, so the next thing, and we're going to come over here. Okay, the next thing would be the always comb. So always underscore COMP. And we need a begin. Actually, let me put the begin over here, give me more space. Okay, now, what I like to do, and you know, this is optional but recommended, is before we start into a case statement, you're going to see that the main portion of this always comb is a case statement. But what I like to do before I start the case statement is initialize my outputs. Okay, and I'll explain the reason why coming up here. But here we have count and LED as output. So after the always comb begin, I'm just going to assign count, or not assign. You don't use an assign statement. You just declare count. Since it's 3 bits. And then semicolon That's the same thing, not a J. And then LED 0. So this here, this is just initializing outputs to 0. So initialize outputs to 0. I'll explain why I do this coming up. I might have explained this already in the early snippet, but in case I didn't know, I'll say it again. Okay, then comes a case statement. And this case statement, we want it to be sensitive to present state, because every time present state gets assigned to next state, right? There's a change. That's when we want this case statement to happen, because the case statement is going to determine where we're going next, you know, what state we're going to next. So it'd be case present state. And now in your case statement, you're just going to put each of the states. State A, state B, state C, state D, state B. So I'm going to start with state A. Okay, so you know, when present state is being assigned to the next state, it changes and it's state A. We need to begin. And now the first thing you put, once you're in state A, or once you're in a state, the first thing you put is what your more output is. Okay, right? Because remember, more outputs only depend on the state. Right? So once I'm in a state, I know what my more output's going to be. Okay, so when I'm in state A, my more output is a binary 2. So I'm just going to put count. Now you use equal signs inside and always comb, like we talked about, right? You don't use the arrow. That's going to be 3 tick mark B 0 1 0. And again, this is a more output. Okay. So now after my more output, now I have to put an if statement to determine, you know, whether I'm just going to stay in state A or whether I'm going to go to state B, right? And that depends on enable, right? So I need an if statement where enable is my variable that I look at. And then also in this if statement, that's where I'm going to have my mealy output, because the mealy output depends on not only the state I'm in, but also it depends on this external signal here, enable. Okay, so after the more output, now it's going to come an if statement. And that if statement depends on enable, right? Because if we're in state A and we have our enable, and I'm going to have multiple outputs here, so I need a begin. Remember how we talked about with an if statement, if you only have a single output, you don't need the begin end within the if. But here, as you're going to see, we've got 2 outputs, so we're going to need a begin. And then LED would be equal to 1. So LED equal to 1. And then if it's enabled, not only does the LED light, but I'm going to state B. So that's where I put next state equal to state B. Right? Because if I'm in state A and my enable input is active, right? If it's a 1, I want to light the LED, right? That's the mealy output. And I want to go to the next state, which is state B. Okay, else, oh, I need an M too. Good thing I have my notes. Right, because you gotta end this begin. Actually, did I end this begin over here? Yeah, I did. That's something that I always tend to forget is and matching my begins. Okay, but then I want an else. Okay, so if I'm not lighting the LED and I'm not going to state B, well, I'm just staying in state A and I'm not lighting the LED. So again, I need a begin here for the else. Then LED equal to 0. And then next state would just be state A, because I'm staying in that state. Right, so I'm not enabled. And then I need to end this. To end. So this end would go at this begin of the if, and then I also have to end the state A. So there'd be another end here for this begin. Yeah, so you're gonna have two ends here. Okay, one's for the if begin, and the other one's for the state A. That's where I always tend to make mistakes. It's like I said, having your ends and your begins have to match. You have questions?
You had 2 begins and 3 ends.
Did I mess up?
Right.
Let's see, there's a begin end here, begin end here, and then begin end. Yeah, but you just proved my point. It's easy to miss. So yeah, if you ever get like, syntax red lines under an end or something, I think it puts it under the end if you have like not enough ends. That's usually the reason. Now, you'll get all crazy type of compiler messages. Like it's not going to say, you're missing an end. But if you got something like that, it's usually what it is. Okay, well, if you understood this part here, the rest is just repetitive because now you just would do the same thing for state B. You have state B and then begin. Now, of course, you don't need to, you don't need to initialize. Well, we initialized before the case. I'm sorry, I'm looking at the wrong thing. But then once you're in state B, now you would put the more output for state B, right? So the more output is all zeros. So you would just have count equal to 3, tick mark 3, all zeros. And then you'd have if again. Right? If enable, begin. Well, when I'm in state B, right, if I'm enabled, I'm not lighting the LED and I'm going to state C. Right, so instead of LED 1, next state STB, you'd have LED 0. And next state, state C, right, so STC. Right, and then you need an N there. Okay, else. Yeah, you need a begin. Okay, else, I'm going to keep the LED off, but I'm just going to stay in state B. Let's see, LED equal to 0. Oops. And then next state, state B. And I have to end that. And then end the state again, right? So again, 2 ends. All right, so I mean, you just keep doing the same thing, right? Then you're looking at state C, state D, state E. Okay, so do you think you could finish this based on these? Because it's just repetitive, right? If you understood how we got state A and state B, it would just be repetitive, same approach for the rest of the states. Now, since you have a case statement, what do you need at the end of the case statement? What's the last thing in the case statement? Like after your options, default. Yeah, so you do your other states and then you'll have a default. And you make the default whatever you want. I made it next state, state A, right? So if I have something funny that happens, right? Like again, if this was on a satellite and they got bombarded by solar flares or something, changing bits around, and wasn't any of the options I had, well, it would take it back to state A in this case. All right, and then of course you need like an end case. End case, and then you need like an end module. You can do the rest. The rest is just end module basically. Is there a question?
The LED, are we like turning it on and off?
Right. See, that's looking at the state diagram here. We're only turning the LED on when the sequence starts and when it stops. Everywhere else, the LED is going to be off. So it's when it's off, we're assigning it to 0. When it's on, we assign it to a 1. So see, I'm just looking at the state diagram. See, wherever it's just LED, that's when it's on, right? Bar LED means it's off.
That's in the L state.
Say that again?
That should be, is that not between the L state or the N F two?
Where are you pointing here?
If N is enabled.
If enabled, see, this is when we're in state B. So if it's enabled, we want the LED off and we're going to state C. That's what this is. Now, if we're in state B and enable is not enabled, then we're staying in state B and we're still turning off the LED. Okay. So again, your question points out that to write the code, you just got to look at the state diagram. Okay, and no matter what kind of state diagram you have, this is the structure of system Verilog when you model an FSM. It's always this structure. It doesn't change. Okay, so that's why I said once you have the state diagram, it's pretty cookbook to go into the code. Okay. All right, now the activity will give you more practice with this. Let me bring up Canvas here in the projector. Just want to point out a couple of things on the activity before you start it. Also, I just want to remind people that the activity from, I don't know how many classes ago it was, but a few classes ago where you need to pull a signal out from an intermediate signal and show it on the timing diagram. Remember, you have till the end of this week. So you have till Thursday to show me that. Show me from lab 4, like, if you want to show me in your lab 4, you can do it, or you can show me in lab 5. It doesn't matter. It's important that you're able to do that because you're bound to need it in this class, next couple of labs, and hopefully your final project. But you also need it for really good system. The resolution's not the best here again, but anyway, this is on Canvas, but there's two things I want to point out. One is on, this is the code that you're given in the activity. So like I said previously, you're going to go the reverse direction. I went from state diagram to code. You're going to go from code to state diagram. But you see right here, I know it's hard to see, but right here, it says parameter, and then it has like 1 to 0 or 2 to 0 for 3 bits. And then it takes each of the states and assigns it a binary number. Like state A is all zeros, state B 001, and so on. And then after that, it has these 2 logic declarations for next state and present state. So this code here is replaced with those 2 lines with the type definition, enumerate, where you name your states. So these lines here are the same, or they do the same thing as what I showed you previously. Okay, after you declare the outputs and before you go into your case statement, that code replaces this. And you see, the reason why it's better to use what I showed you than what's on this activity is because if you have to go in and edit your code, like, you design it, you think it's designed correctly, this is going to happen in CPE133, guaranteed. You do your control unit FSM, you think you got it all right, and you go to sim it and it doesn't work, and you start editing. Well, if you have your states defined this way, well, if you add states where now 3 bits isn't enough, because maybe now you have more than 8 states, right? Maybe you've gone into 10 or 11 states. Well, if you have your states defined this way, you have to go back in and you have to renumber things. Where if you define the states the way I have up on the board, the software takes care of it for you. Okay, like you don't have to worry about assigning these binary numbers to the different states. Okay, so that's really the convenience of using that type definition with the enumerate. Okay, also the other thing is, it's also more convenient when you troubleshoot, because when you use the enumerate way of declaring the states on your timing diagram, the states will show up as you name them. You know, be like state A, state B. You can see it right on the timing diagram. If you use this method, the states are going to be binary numbers. And like everything else on your timing diagram is binary numbers, and it can get confusing. Okay, so anyway, I just wanted to point out the difference of the code. Now, the last thing, unless there's questions, I just want to show you something, the solution to this. Okay, this is the solution to the activity. And the thing I want to point out is that you can see here in the state that now, here's our legend. So in the bubble here is Z1. So what does that mean since it's inside the bubble, Z1? That's a more output. Z2 is outside the bubble. That's a mealy output. Okay, good. And you see here are our external inputs, X1 and X2. And this is a clear, which is the same as reset. It's an active load clear. And then up here is just the name, right? So again, they're named state A, state B, state C, and so on. But the thing I want to point out, and this is something that came up during Carnot maps, but people tend to forget it. What does a dash mean? See how there's a dash and then this is X2, not X2. What does a dash mean in Carnot maps? Yeah, it means don't care. It could be either, right? Same thing here. Like you can have an input that doesn't matter. It doesn't have an effect. Like in this particular case, the transition from state A to state B, only X2 matters. Okay, so if you have an input that doesn't matter in a state diagram, you use a dash. That's like you use a dash in a Carnot map when something doesn't matter. Like an output doesn't matter, right? Okay, so that's the game plan for today is, you know, work on this activity as a table, just like you've done. Once you're done with the activity, the next priority is lab 5. Has anyone finished lab 5 by chance? I wouldn't think anyone has. Okay, lab 5 is the next thing to do. Also, remember to show me that you can drag a signal over and show it on the timing diagram, because that's an activity from like a week ago that most people in here still have to get checked out for. I think only about half the class I've seen. Okay, and yeah, you won't be able to start lab 6 yet, but like I said, lab 6 isn't due till end of next week. But after Thursday's class, you'll be able to do lab 6. Okay, so any questions before you get started? Right.